Okay, this is not on your textbook, but this is also very important, and so I want to talk about that. Let's see, we all know the definition of terms: a catalyst, enzyme, substrate, inhibitor, so be it. And one of the representative reaction for enzyme reaction. Enzyme, the characteristics of enzyme is they don't change, but they will make change of the other stuff. And if enzyme is there, S can turn to P, and that's the role of enzyme. Okay. But what I'm trying to do in here is, I just want you to pay attention to the reaction. So it's not really a big deal. And this is ES, and I will also talk about E and P. And for to express concentration of ES, so we know, and we have something. This is this is supplier, and this is kind of this is supply, this is demand. So in this case, if we have a K1 reaction that goes in here, and K2 is kind of reverse reaction, and K3 is kind of reaction that goes forward, and if we say K4 is reverse reaction. And then from the point of ES point of view, I want you to ignore this one, okay? And something producing can be, let's say, expressed like this, okay? Let's say we know that, okay? We know that. And then this is something plus, gaining something from here to here, so this is plus right here. And something goes away, and then it's from ES, that becomes K2, and some becomes K3. So, and if we have a steady state, equilibrium, and that means going forward and going backward, they are the same. In this case, we know, and also in here, something producing also can be there. And let's say this one can be E and P. And equilibrium means my ES is constant and at equilibrium. That means if I differentiate this one, this means it's 0. Right? Okay? If you differentiate constant, you will get 0. In other words, I will have this one, 0. Then I will just put everything plus in this part. And I don't think I need to repeat that. And it equals K2 plus K3 and ES, right? So I have things like this in here. So I will calculate the enzyme reaction and enzyme concentration ES. And in here, by using this equation, I can have a K cube and K plus right there, right? And I can have E. So if I play with this equation, I can have this kind of relationship. Okay? No problem. Right? Okay, then usually this kind of inverse reaction is very small. So if we let's assume this one is very small. So I can neglect the term in here. Okay, cancel. K4 times P is nothing. Or just ignore that part. Then I have only K1 plus S here. And then my total, my E and ES, in the initial state, I have no ES. But when we start the reaction, I start to have ES and then E plus P. So if I can, my initial E was there, and it was split into E and ES when we start the reaction. So we can write my E total is E plus ES. And in this case, the only way that we can write this in this way is different from NH4 and NO3. And if you think about total nitrogen is, I said, total nitrogen is the summation of organic nitrogen, ammonia nitrogen, and NH4 and NO2N plus NO3N. In this case, if I had a 18, which is 14 plus 4, if I have 14 plus, let's say, 16 times 3, 48, and then 62, right? If I had total nitrogen, which number do I use? Is this, in other words, if I have an H4 in this 18, if I have 3, do I have 62? No. You got to have one N, which is 14. You got to have one N, which is 14. You just count nitrogen only. Okay? Well, in the middle, during the reaction, it can be with the hydrogen, with the oxygen, with carbon, whatever. We don't care. If I want to count nitrogen only, I only care about nitrogen here and there. In this case, if I have one N, then I have one N. Just like the stoichiometry, right? If we don't follow this rule, then we will be nowhere. Because if you just keep just thinking about total weight, then the reaction, formal reaction is going to be different in every different time. So it's going to be very difficult for us to follow those values. Okay? So when we talk about nitrogen, and we will talk about nitrogen only. In this case, same thing. In the E, I don't know what is the E. That can be N or that can be C, whatever. Okay? But in here, I only talk about N, if there was N. Okay? So if this was somehow, and let's say I had 3 of this one, and somehow I have 2 NO3 something and 1 NO2 something, and I must have some other stuff to keep the balance in the right hand and left hand side. Still, if I have 3N here, I have 2N and 1N and 3N. That's it. Okay? So in this case, 1 is, and still there is the possibility that maybe this can be like this 2, because this one still needs to be converted to NO2 and NO3. Then I have 1 N, just 3N. Okay? So in this case, my original material still can be there, but some NH4 got converted to NO2 or NO3, whatever. Okay? But still, my total nitrogen is the same. Okay? Because I'm talking about inside the water jar, where I raise my fish. So my E can be here, and then if I move to my ES over there, then my E can be expressed like this. Okay? So what so far what have I and major story that I want to tell you now is I don't want you to remember this equation. Okay? This one can be like that, cannot be like that. It's okay. It's okay. And I don't know what is E, I don't know what is S. I don't care. Okay? I just want you to know how do we just change equation and how I just want you to show the scientists or engineers what they do usually when they have data and try to find out equation for their data. Anyway, so I had this from now on is purely mathematical, and I had a K1 S, and instead of E, I have a ET minus ES, right? And ES, and it's like something like this. And what? Okay, then I somehow want to use this equation to express my ES. You may think, why that professor is talking about like that? Don't worry, don't worry. We don't care about E, we don't care about S, I don't care about ES, whatever. I just want to know the form of equation, right? So ES somehow is like K2, K3, and K1 plus S and ET S. Okay? If we can somehow substitute these three values with this Km, then we can come up with this. And I just want you to take a look at this only now. And also I want you to take a look at this equation as well. Is this familiar to you? No? 강호 교수님하고 생물학 스페셜이 들었습니까? Have you taken wastewater treatment plant biological? And have you seen the growth rate of bacteria in there? Now you remember that? Okay? This is the most famous equation that is used to express growth of bacteria. It's called as Monod equation, according to the first developer of the equation, and he got the Nobel Prize. Nobel상 받았어요. So the reason I am trying to show this kind of process is they are very much similar, and then this is the equation, not from theory. This is from trial and error. In other words, empirical. But he must have gotten his idea from this kind of reaction, because he has studied this kind of stuff more, or long, very many times and occasions. So it must be pretty natural for him to find out, to come up with this kind of suggestion or equation to express the growth of bacteria. Now, so that's the most famous Monod equation. And once you are good at one class, and it's going to be a lot easier for you to study other classes in our department because they are all connected to each other. You saw that I'm talking about PC-pH diagram, right? That you learned from water chemistry. Now I'm talking about growth of bacteria that you learned from biological wastewater processes, right? So, bacterial growth. This is growth rate. Kim Chun-chin, my favorite baby. When I say rate, what we are talking about? Time, right? Rate is about time. Okay, then this must be like in the case of first order reaction, we had 1 per day. Now we have Ks plus S and mu max and S. S in this case, in our secondary treatment, usually is BOD concentration. If you have this much food, in other words, this one is food for bacteria. Okay? And if you have this much food, then bacteria can grow that much. So if we draw a graph between S and mu, and if you have a 0, your growth rate is 0. If you have no food, you have no life. As soon as I start to have my S and your mu becomes bigger and bigger and bigger and bigger, and if I have more than enough food, then this Ks may be pretty smaller than S, then we can simply have equation like this, then we can simply cancel these two. Then what does that mean? That means they will reach to a maximum growth rate. Okay? Well, this time can be very long. I don't know. It doesn't. Sometimes it can happen in a few hours, in a few minutes, in a few seconds. But I will just have to say long enough time anyway. Okay? And let's take a close look at this equation again. Mu max S. And I want you to pay good attention to this denominator. And if S is small, if S is small, mu is like the mu max Ks and S. In other words, the first phase is like a linear line, and my slope is mu max over Ks. Right? If you have so much S, then you will have this one. I said we can just cancel these two. Then this one will breach because this one is small, so we'll disregard this one. And then if S is big, my mu is just mu. Okay. And then we have to also talk about part right here, what is Ks? We call this Ks as half saturation equation. And dependent on K, this K will determine if my graph is like this or like that. If you have a small, if you have a big K, this is a big K. This is small K. If your K is big, your graph is like that. Okay? And we say, okay, this is 0.5 mu max, half of the maximum growth rate. And if you have, let's say, I will use this curve anyway. And my unit of Ks must be the same as my food, which is BOD. So BOD concentration, there is milligram per liter. So this one must be milligram per liter too, right? So my Ks must be in this axis. So I will define my Ks is the substrate concentration that can make my growth rate exactly the half of the max. That's why I call half of saturation. Half saturation. Very, very much important. And when you talk about algae, algal growth, and when you talk about food of algae, that's phosphorus, right? Or nitrogen, we'll talk about the same stuff. Exactly the same stuff. Silica, nitrogen, phosphorus, whatever, or light, or even temperature, and then we will use that equation. So that equation is very much important. And when you calibrate means try to adjust your curve to your data, and then we will play with Ks and Unix. We will find those values by using trial and error. So those are some values found in the literature. So for nitrogen, and those are the scientists or scholars, and they use this kind of value for Ks. They are different because this one is captured by Whiteside. They are different from case to case. So I want to, but the shape, the form of the equation is the same, right? So for nitrogen, this is for algae, phytoplankton growth. In this case, this is for bacteria in your secondary treatment plant. Same, exactly same. All right. I don't think I will cover that. I will cover this one, and I will just finish. Okay. In here, we are talking about dependent on pH. NH4 plus NH3 they can have a different form. And let's say this one is right here. It's because of ammonia. It's A. Let's say this one is A. This is B. And this is your reactor. This is your, let's say, pitching. And you have a water jar, right? Something coming in, something going out. And in here, A only. Again, what I said, dependent on pH. My ammonium can be in a different form. But ammonia, they can escape from water by volatilization. But NH4, they cannot go. They cannot go. They don't have that kind of characteristics. They just stay in the water. So in this case, something coming in shift here. We can talk about it later. We're just, for now, I'm not going to talk about that. But in here, for NH4, let's say this one is B, right? And this is NH3, H plus. This one is A, H plus, right? So, and then for if you are in this jar, and for D, let's say D, dt, and you are losing your B because of K, F, and B, right? And also, in this case, B is lost because they can be in here. I didn't write it in a good way, but this one is transformation. This is 90%. And also, if there is some kind of reverse reaction, then there can be some KB, A, and H. This is possible, right? For dA, dt, and they can gain the mass because of this reaction, because this one goes to A, this one must be go there. And then also they can exact the same amount must be there. Also due to volatilization, and my A is gone. Right? So I have not talked about this part yet, but we can talk about it later. So for now, I just want you to ignore. But in here, we have very strange stuff. Everything was multiplied by V. And in here, all of a sudden, we start to have AS. But it's okay. It's okay. It's okay. And we can talk about it later too. Because usually volatilization is the function of your area, not the volume. That's why we have that one. But we can. There's always a way that you can use the same style. So it's okay. So in here, is this in our exercise, by the way? No. Okay, that's fine. I think we have temperature somewhere. So yeah, I will talk about that much, and I will just skip everything over here because these are too much complicated. I want you to just keep it and read it over when you need it. Because time has not come for you. Alright. Alright, for the temperature, usually we have the, if we know the reaction rate at 20 C, then reaction rate in any temperature can be expressed like this. We call that as Arrhenius equation. Okay? And I want to, though there is some way to drive this one, but I only want you to remember this one. And this theta is called as temperature correction factor. Well, for example, if theta is 1.072, for every 10-degree difference, the theta to the power of 10 becomes 2. Okay? So I want to solve equation 2.5. But this one tells us that if we use this kind of equation, if we have bigger theta, then you have more effect of temperature. Okay? So it means if you are a microorganic bacteria and for higher concentration, you will become more active. But what about 100 C? If you got boiled, are you going to be still alive? That's the question. So in that case, we cannot use this type of temperature process factor, right? Because bacteria, biological entity, we need a certain kind of temperature that we like. For me, I like between 20 and 25. Okay? I don't know about you. Maybe somebody like the cooler temperature. Somebody like warmer temperature. So I think this is one of the good or the classic way to show temperature effect. But this is not the only way. So we always need to think about that. And nowadays we have another function like this, dependent on what this is t minus t something squared by the way. So if I draw that function graph, and my ft is like gonna be like this, or I have a tm1, tm2, then I have this, and like a trapezoidal or like a mountain. Because in here, I like it. I feel good. If it's too cold, I don't like it. Too hot, I don't like it. I think this is a better situation to express temperature effect. So this is a little bit funny looking, but anyway, if I have just one optimal temperature, then my shape will be like this. But I like this one a lot better. I like this one. But usually Arrhenius equation is the most popular equation that you can use as a temperature effect. And I have many equations for you. You can have fun, but I will skip those over, and it's not a good time for us to talk about that. But you can come back always, and those are babies that you need to take care of. Bye. This coming Monday. Good luck. Have a nice day.